Hi everybody, we're going to do a short lesson on intro to matrix operations. Before you watch this video, please make sure you either have the handout that you got in class or you have printed off a blank note sheet from Schoology. You should take notes along with this video. Okay, so let's do some definitions here, and then we'll get into actual matrix operations, combining them in different ways. So a matrix is just a way to arrange numbers. We would say that it's a rectangular arrangement or array of numbers. Could just be plain old numbers. It could be some sort of parameters that you're given. Could be variables. Okay, so it's a way to collect and arrange and organize a bunch of different numbers. Now those individual numbers, so if you kind of glance down the page there's a bunch of numbers floating around in here. The individual numbers are called elements. And sometimes we want to pinpoint a specific element. So let's just put a little example here. Now, your matrix most often will look something like what you see on this page with a bunch of numbers and rows and columns. We could have some letters that we throw in there, and let's go across the rows here. Maybe something like this, A, B, C, D. If we want to talk about a specific location of that element, we might have something like this. Element A that's in row 1, column 1. So that's not meant to be 11, that's a 1 and a 1. This would be the element in row 1, column 2. This would be the element in row 2, column 1. This would be the element in row 2, column 2. And we can keep building that bigger and bigger. It doesn't have to be just like a 2x2 matrix. Now the other way to name a matrix, instead of writing out all the individual elements, we might just have a little tiny matrix with a capital letter in there, because sometimes we want to just work with them generally and not all the individual pieces of it. Super important idea you need to know related to a matrix is what its dimensions are. How big is it? How many rows? How many columns? We always describe a matrix by the number of rows first, by the number of columns second. So rows by columns. Okay, abbreviate that if you want, R by C, rows by columns. If you're like me and have to pause and think, which one is which again? I always go back to, like in Greek architecture, those beautiful columns stand tall up and down, right? Rows are going across. The other thing that might, I don't know if this still exists, is RC Cola, still a pop that you can buy. That helps me just remember that rows come first, columns comes second. Oh, and then one more term you might see. If a matrix has the same number of rows as columns, we call it a square matrix. So the number of rows would equal the number of columns. Just put a box around that to separate it. Okay, so here's a bunch of examples here. We've got a 2x3. This is where, can I just show you where my eyes go when I'm trying to determine the dimensions? Because this is a really important piece to be able to do. I always start kind of in this bottom corner and I go up and I count how many rows are there. So 1, 2, and then across 1, 2, 3. That's a 2x3. As opposed to a 3, right? I'm going up first. I pass by 3 rows and then across 2 columns. So there's a bunch of examples there, and then you can see a square matrix at the end. When you are adding and subtracting matrices, you just have to make sure they're the same exact size, because all you do is add corresponding elements. Okay, so let's make just a quick note here. They must be the same size. You're just going to basically imagine you could put one on top of the other, add the numbers that are one on top of the other. So I would be adding 5 and 4, and I'm going to get a resulting matrix that's the same exact size. So let me backtrack for a second here. This is a 2x3, right? So this is a 2x3. This is also a 2 by 3. My result is going to be a 2 by 3. So let me go back to adding here. I'm going to add 5 plus 4. That's going to give me 9. You can decide on your own if you want to go across the rows. I like to go across the rows first, or if you want to kind of go up and down each column. That's up to you as you're doing an example like this. Next, I would add a 2 and a 6, and that would give me 8. I'm only circling them so you can see them matched up. And then we just work our way across. So 15 would be my last element in that row, and then I would have 6, 4, 12. Okay, I want you to pause the video for a second, subtract the next one, and then come back in a minute and see the result. Okay, so go ahead and pause. And let's compare answers real quick. You should have across the first row 2, -2, and then second row -3, 1. The 2 by 2s that I wrote at the bottom, that's not part of the final answer. That is just, okay, I'm making sure that they're the same size, and I want to make sure that my resulting matrix has the same size as well. Okay. You're going to see some words. They're going to ask about, are these matrices commensurate for addition or subtraction? Basically, are they compatible? Are they able to be added or subtracted? And actually, we'll get to multiplication in a second here as well. Okay. Do the dimensions match up in such a way that you're able to do those? Okay, the next part, scalar multiplication, is, I kind of think of distributive property when I'm looking at something like this. So example 3, that 5 that's outside is called the scalar. I'm just going to make all of those numbers inside 5 times bigger. I'm not concerned about the size of that matrix at all. I'm just going to take every number in there and multiply it by 5. So instead of 2, 3, 4, I have 10, 15, 20, and then 30, 5, -35. Same exact size as what we began with. Now you can see all of those numbers have gotten 5 times bigger. So again, go ahead and pause and try example 4. Just watch your plus or minus signs on this one, and you're welcome to leave those decimals as fractions instead. Okay, so that's adding and subtracting. That's scalar multiplication. Now we're going to get to, and this is a little bit trickier, I think, actually multiplying 2 matrices together. Here's the first thing you need to check. Are they compatible or commensurate for multiplication? And the way that we tell that is based on the dimensions of the matrix. So let's look at example 5 here. This is a 3 by 2, and then we have a 2 by 1. Here's what you're looking for. These 2 inner numbers have to be the same in order to be able to go through this multiplication process. So the number of columns in the first, the number of columns in matrix 1 must equal the number of rows in matrix 2. But I just find it easiest to write those numbers, those dimensions right below the matrix, and just make sure that the middle numbers match up. Now, the reason that that has to happen is because of the way that we're multiplying. I want you to think of, we're going to take one of the columns from the second matrix. So let me just outline this column here. Now, there's only one this time. And we're going to kind of spill it on top of these rows. Okay, one row at a time here. So I'm going to take this, and if you want, you can even put the 5 and the 9 on top. Now, this is a totally different process than you have seen before. So that product that we're going to get right here, oh, by the way, here's a little kind of sneak peek at where we're heading. Those outer numbers, these right here, tell us that the result will be a 3 by 1. So our final matrix, if that helps you organize things, you're going to have, let me make that a little bit longer actually, 3 rows and just 1 column. Should maybe mention that first. Okay, 3 rows and 1 column. Okay, so here's what we're going to do. Now we're multiplying, but we're multiplying. This reminds me of that, like sum of the pairwise products thing, because we're multiplying, but we're also adding at the same time. So we're going to do this product here, 5 times 1, plus, scoot this over, this product here. And all of that will turn into just one number, 5 plus 27. Let me maybe simplify that as the next step. Again, my final answer will just be 32, that one single number. Okay, now let's do that again where we're going to work our way down. So now, let me keep that green one highlighted here. I'm still taking, actually let me reset for a second. I am still taking this column, and I'm going to spill it on top, but now I'm working down to the next row. So I'm going to put the 5 and the 9 still on top here, but now I'm multiplying here and here. So my next product would be, or my next element would come from 5 times 2 plus 9 times 8. 5 times 2 plus 9 times 8, which would be a 10 plus a 72, or final answer here, 82. And then we just work our way down one more. Let's see if I can just scoot this down now. Okay, so now I'm doing, where's this? I'm taking the 5 and the 9, I'm spilling it on top, and now I'm multiplying these pairs. So I've got a 5 times 4 plus a 9 times 0, or a 20 plus 0, or just 20. Here is my final matrix, and again, note that it's a 3 by 1. I think you'll get 3 numbers out of there, but sometimes it's tempting to make it a 1 by 3, like make it go this way, kind of long that way. Just pay attention to, again, first rows, then columns. So I'm going up 3 rows and over just 1 column. Let's try another one of those. We'll work through kind of piece by piece here. Okay, so for example 6, let's check our dimensions first. This is a 3 by 3. The second one is a 3 by 3. Middle numbers match. We're good to multiply. Outer numbers tell us that our final product is also going to be a 3 by 3. All right, so we're going to take this column here, spill it on top like this, 2, 1, and multiply this row. That will look like, give yourself a little bit of room to build this whole thing out here. Negative 1 times 2 plus 2 times 4 plus, what was that, a 1? Yeah, 1 times negative 3. All of that will eventually become one number. Maybe I'm going to put my 3 by 3 on the bottom here when I'm done. So I've got a negative 2 plus an 8 plus a negative 3, which all would turn into, what is that, positive 3. Okay, now watch, when we work our way down, so I'm working with this column here, but now I'm going to work my way down. Apply these pairs. Now I'm also scooting down over here, so this is a negative 1 times 5 plus a 2 times 1 plus a 1 times 2. And then let me just keep going here. I'm going to just scoot my way down here. Negative 1 times negative 1 plus 2 times 3 plus 1 times 4. Okay. It might be a good idea to at least do kind of one set at a time and then simplify your numbers so you don't, I felt like I was maybe jumping around too much if I simplified all at once. Now this is just the first column that we built, right? Because we used the first column here. Simplify those. We end up getting a negative 1 from that second set, and then I think an 11 right here. Now we're going to repeat this whole process, but scoot over to this column. Okay, so now I'm going to spill the 3, 4, 0 on top and just work my way down. So this next one looks like, I'm going to change colors here. 3 times 2 plus 4 times 4. By the way, if you want to just make those 6 and 16 and 0 right away, you're welcome to do that. I probably would do that on my own this next time through. And then we work our way down. 3 times 5 plus 4 times 1 plus 0 times 2. Okay, I'm going to pause, or you're going to pause in a second. I want you to do the rest of that multiplication all the way through, and then come back and check your answer. Okay, go ahead and check final answer. If my color coding is helpful there. Where my circled rows and columns are here, that was sort of the last place that I ended, was this third row, third column. This is hard. Oh, I shouldn't say it's hard. It is a weird process. It just takes some practice. Okay, so which you'll get a chance to do. You'll do a few more with that. But this is definitely the hardest part of this section, is multiplying those. Okay, one last piece here. It asks about the order of multiplication. Does that matter? Do you remember the commutative property? That means that the typical commutative property of multiplication says that whether you do A times B or B times A, you would get the same result. That is not true with matrices. The first issue we may run into is that the dimensions could get messed up. If you're multiplying initially, let's say, a 3 by 2 and then a 2 by 1, that one works out fine. But if you switch those around, did a 2 by 1 first and then the 3 by 2, notice these inner numbers are not the same. So that's an issue we could run into. But even in square matrices, you get a different result because you're matching up the numbers in a different way. Let me just give you the answers here for this one. If you did A first and then B, so multiply them in the order that you're in, you end up getting across the first row 12, 13, and then 24, 25. You can try that. That would be a good place to kind of pause and practice. Make sure you can get those values. But when you switch them around, let's say you put B in front and you were spilling the columns onto B, the columns of A onto B, you end up getting, I think, -3, -4, and then 27, 40. So it's not even like, oh, the numbers are in a different spot. You get totally different numbers anyways. Okay, so the dimensions work out fine. They're all 2 by 2s. All those numbers match up, but you get a different result. Okay, and then the last piece of this is something really important called the identity matrix. It's just like the number 1 in multiplication. It sort of serves that same purpose. So let's write that down first. It's like number 1 in terms of how it's used in multiplication. So here's what the identity matrix looks like, and it can be different sizes. You could have a 2 by 2 identity. Sometimes we write it like this. Oop, I will pause and come back to you. The bell just rang for your class. Okay, sorry for the little pause there. Okay, so the 2 by 2 identity matrix looks like this. It's a 2 by 2 with 1s along the main diagonal. Highlight what that looks like. So that's this diagonal here, 0s everywhere else. Okay, that I want to circle that, maybe main diagonal. We'll see that term later in the chapter. The 3 by 3 identity matrix, by the way, it's always a square matrix. It must be a square matrix to be an identity matrix. Same rule, 1s along the main diagonal, 0s everywhere else. So think about where those 0s would need to go, how many we would need to be to still get a 3 by 3. And you could keep doing that for a 4 by 4, 5 by 5, etc. Now here's why, what we're going to do with the identity matrix. Now I mentioned that it's just like 1 in multiplication. So think about if you were doing, some number times 1 or 1 times some number, you always get that number back. The same is true with the identity matrix. Let's say you take a matrix called A and by the identity matrix. Now this is an exception where the order doesn't matter. I could put the identity matrix first and multiply by A, but both of those would result in just giving me matrix A back. If we think about, and we're not going to go through the whole process, but you're welcome to do it on your own. If you think about multiplying these two matrices here in example 7, let's walk through our process again. I would take this column and spill it on top of the other matrix. Look what this is doing. 4 times 1 is keeping a 4 in that position, but then the zeros here are kind of wiping these numbers out. So it keeps the 4 intact that was as part of, that was in that position initially. And then the kind of the same thing happens. Ones keep the numbers intact where we want them to be, and then the zeros wipe themselves out. Back, I'm just copying down the matrix that's there. If you really have the identity matrix, you really don't even need to go through the process. If we switch them around, the same thing happens. You're welcome to go through and try that process and kind of see what that looks like. Okay, feel free to rewind, rewatch any parts that you need, and then please try on your own the next page of the little handout, which is just 1 through 10. Now, we will do a lot of this in the calculator, but it is important that you understand the process behind these different matrix operations. So give these a try. I will have the answer key to this posted on Schoology. Please look over them. The expectation is that you come into class tomorrow with any questions that you have with these practice problems attempted and checked, because we will just jump into the next lesson then. Okay, please reach out if you need anything at all.